By now, you have heard the phrase that energy cannot be created, nor can it be destroyed. Did you ever think where that scientific law originates from? If you have, then you got your first glimpse at the rabbit hole, which is thermodynamics. The first law of thermodynamics states that the energy of the universe is constant, thus implying that energy indeed cannot be created nor destroyed. Energy is conserved.
In a Newton's cradle, gravitational potential energy increases from when I pick up the metal sphere and transfers towards kinetic energy when I release, which travels through each sphere until reaching the sphere to the right. The sphere to the right raises in height and potential energy, thus repeating the process and conserving the system's energy.
Our universe began after the Big Bang with a constant amount of energy in a certain amount of space. But in our universe, space is constantly expanding. So what happens to the same constant amount of energy? Now we relate the concept of energy in the first law of thermodynamics to the second. The second law of thermodynamics states that in any spontaneous or favored process, there's always an increase in entropy of the universe. Entropy is the probability of different microstates or positions of particles that can occur in a given space. In other words, though, entropy is the measure of how disordered particles are. But how is entropy always increasing in our universe?
Let's use tennis balls to demonstrate this idea. As we start with 3 tennis balls, they represent the finite energy of the universe applied to particles, and the cylinder they are in represents the initial space in the universe. As I apply a shaking force to the container holding the tennis balls, the balls don't move much. Thus they occupy relatively few positions and have low disorder. However, if the same number of tennis balls are placed into a bin which is larger than the cylinder, this represents the same finite energy of the universe interacting with more space from the expanding universe over time. As I shake the bin, the tennis balls move around a lot more, occupying more positions compared to the previous demonstration, increasing the entropy in the system.
Therefore, as the space in our universe is constantly increasing, like the container size in the examples, the finite energy in our universe, or the equal number of tennis balls in the containers, will have to spread further over the greater space. As the energy with the tennis balls spread further over the always increasing space, there are more possible positions for energy-filled particles to travel through. Thus, the entropy in the system will always increase. Eventually, our universe will expand to a maximum amount of space and stop, where there's essentially a constant energy of 0 spread across the universe. What happened to entropy if the energy in the universe is 0? Well, that covers the third law of thermodynamics, which states that the entropy of a perfect crystal at absolute 0 is 0.
Let's use the bin again with the tennis balls, as they would represent the particles in space. If I don't shake the bin, then I am not applying any energy to the system. Thus, the system is in a state of absolute 0, where there is no energy. The balls do not move, and they cannot travel through different possible positions. Therefore, they are in their most organized state, in other words, their lowest possible entropy. The entropy in such a system would be 0 relative to its other possible entropy states, since it's the lowest. Scientists have come really close to absolute 0, with 0.0001 Kelvin.
Maybe now with your new understanding of thermodynamics, you can think about the ever-expansive effects on both a cosmic and microscopic scale, because energy is all around us, but we only have a certain amount of energy in our expanding universe. Let's not waste it and use it to fuel our future learning. Thanks for joining.